These slides deal with the central limit theorem for graphs or finite abstract simplicial complexes. The main result assures that the spectral measure of the Laplacians converge under barycentric refinements universally to a measure which only depends on the dimension of the complex. We restrict in this exposition mostly to graphs. One reason is that the first barycentric refinement of a finite abstract simplicial complex is always a finite simple graph equipped with the Whitney complex defined by the set of complete subgraphs of a graph. The set of complete subgraphs is then a collection of non-empty sets, which is invariant in the operation of taking non-empty subsets. In other words, it's an abstract finite simplicial complex. Hassler-Whitney got his PhD in 1932 at Harvard in the field of graph theory under the guidance of George Birkhoff. Whitney was one of the pioneers of modern geometric analysis, introducing manifolds, proving the embedding theorem, and pushing forward algebraic topology, among other things. He also saw the importance of mathematics education. The picture shows Whitney teaching differential equations. The year is 1931, when Whitney was a graduate student. The topic we deal with belongs to combinatorics and topology. Jean Dieudonné once wrote that there were three essential innovations which launched combinatorial topology: barycentric subdivision, duality, and incidence matrices. We touch upon all these parts. We look at the barycentric subdivision limits of operators defined by incidence matrices. Duality enters because barycentrically refined simplices converge to geometries having more and more Euclidean structure, but we deal here with rather general complexes for which Poincare duality does not hold. The barycentric refinement of a complex takes the faces of the complex as vertices of a graph. The new complex is then the Whitney complex of the graph, in which two faces are connected if one is contained in the other. Here we see an example where the complex is the Whitney complex of the house graph. The 5 vertices, the 6 edges, as well as the triangle form the new vertices. Look at the triangle, which contains the vertices capital A, B, C, and edges called the lower faces A, B, C. After the refinement, the triangle becomes a vertex, which is at the center of the hexagon. The one-dimensional loop attached to the triangle has doubled in length. It now has length 8. Here's an example where we see a complex being refined a couple of times. The complex is the Whitney complex of a triangle. The slide shows the first 4 barycentric refinements. The 4th refinement already contains 1296 triangles. We can compute the cardinalities of all these simplices as the 3 vector containing these data is every time multiplied by a concrete 3 times 3 matrix shown to the left. And here is an example where we start with a tetrahedron, a 3-dimensional complex. The complex consists of all non-empty subsets of a 4-point set. And doing refinements, the number of faces explodes exponentially. The f vectors, which encodes the cardinalities, grows in an explicitly known way. We see the 4 times 4 matrix A, which maps the f vector of a complex to the f vector of its barycentric refinement. We only would need 135 refinements of a tetrahedron to reach a simplicial complex, for which, if the entire complex were the universe, where the individual pieces have the size of a Planck volume, we need then to cover 10 to the power 185 scales, which is less than 24 to the power 135. As another example, we see the refinement of the smallest 2-dimensional sphere, the octahedron. Again, like for the triangle, the number of faces gets multiplied by 6 every time a refinement step is performed. The polyhedron G3, seen here in the last step, has already 866 vertices. Of course, Euler's gem formula V minus E plus F is equal to 2 for 2-dimensional complexes assures that the number of triangles plus the number of vertices minus the number of edges is always 2. The invariance of this number is reflected in the fact that the transpose of the matrix A is an eigenvector 1 minus 1, 1 to the eigenvalue 1. This illustration shows how the lower dimensional parts become less and less relevant in the limit. We started with a house graph G, which has a single triangle. That triangle has exploded much faster than the one-dimensional piece. The number of triangles gets multiplied by 6 every time. The number of edges in the one-dimensional curve only doubles in each step. The lower dimensional parts become irrelevant in the limit when looking at them on a spectral level. We look now at the spectrum of the Kirchhoff Laplacian. Any self-adjoint finite range Laplacian would work too. We could take the Hodge Laplacian or connection Laplacian, for example. The Kirchhoff Laplacian is the discrete analog of the scalar Laplacian in calculus. This is the divergence of the gradient, which can be written as d star d, where d is the exterior derivative, the discrete called incidence matrix. Introduced in 1850, it is just a matrix B minus A, where B is the diagonal matrix containing the diagonal vertex degrees, and A is the adjacency matrix of the graph. By the way, the Kirchhoff Laplacian of a simplicial complex is defined as the Laplacian of the graph, which has as the Whitney complex the barycentric refinement of G. Gustav Kirchhoff introduced this Laplacian in 1850. Kirchhoff was a pioneer in the type of combinatorial analysis and also a forerunner of algebraic topology. One of the Kirchhoff laws can be interpreted as the d square is equal to 0, meaning, for example, that the curl of the gradient is 0, that the divergence of the curl is 0. A contemporary of Kirchhoff was Enrico Betti, who wrote an important paper in 1871. He and Henri Poincaré introduced the incident matrices D, and so essentially built discrete calculus and combinatorial topology as we know it today. The case cohomology group is the kernel of the dk derivatives modulo the image of dk minus 1. Its dimension is now called the case Betti number. If you plot the eigenvalues of the Laplacian of a two-dimensional complex after it has been refined a couple of times, we see this picture. It does not matter with which complex we start, as long as there is a triangle present initially and no three-dimensional simplex was present when we start, the picture will look like that. The graph is scaled so that 0 represents the lowest eigenvalue and 1 is the largest. These continuities correspond to spectral gaps in the limiting density of states measure. If you look at the inverse of the spectral function f, we get the integrated density of states of the Laplacian. It is the cumulative distribution function in probability theory. Its derivative is a measure called the density of states. It is a measure whose support is the limiting spectrum. It is the analog of the probability density function, or more generally the law in probability theory. We don't know yet what the nature of this measure is in dimension larger than 1. We see here the two-dimensional case. Is it singular continuous or absolutely continuous? Or can it even have discrete components? Historically, the spectral picture has first been drawn in a paper I call the Barycentric paper from 2012. We have realized and proven in 2015 that whatever two-dimensional complex we start with, we end up always with the same picture. This is what these slides are about. Here are two example runs. On the left, we look at the barycentric refinements of an octahedron. On the right-hand side, the refinement of a two-torus. The spectral functions look almost identical. I was a little bit surprised. We thought that the topology would matter in the limit, but it didn't. We can prove for any initial complex that the spectral function converges in the L1 norm and that the spectral measures converge weakly, which means in law to the universal limiting measure, which only depends on the maximal dimension of the complex. Here are examples of spectra of one-dimensional circular graphs where the eigenvalues are explicitly known as Fourier diagonalizes is the operator. This is the case which we completely understand already. And here we see the explicit eigenvalues in this one-dimensional case when refining a circular graph with 4 vertices. The reason why we can compute the eigenvalues explicitly is because the discrete Fourier transform diagonalizes the Laplacians. The limiting distributions look the same for any one-dimensional graph, a graph with at least one edge but with no triangles. The distribution is essentially the potential theoretical equilibrium measure on the Julia set of the quadratic map z goes to z square minus 2, which is one of the integrable cases in the sense that we have explicit formulas for the density of states. Another integrable example is the case c is equal to 0, where the Julia set is the circle and the field in Julia set is the disk. This case could be seen also as a barycentric limit in the directed graph case. To the right, we see another Julia set, the so-called dragon, which, however, does not appear as a limiting distribution of the complex. The Julia sets we deal with in this work are the boring ones. Here are two pioneers in the field of iteration of rational maps. To the left, Gaston Julia. To the right, Pierre Fatou. The Julia set and the Fatou set, which is the complement of the field in Julia set, are usually heavily entangled. Two unusual photographs of Michel Audin's book on Fatou, Julia, and Mordell. To the left, we see Julia in a photo taken by George Polya. To the right, Fatou as a kid, a photo from the Fatou family album. In the one-dimensional case, we deal with the equilibrium measure on the Julia set. Actually, the map is Tx equal to x times 4 minus x, which is conjugated to z squared plus 2. The spectral function fx satisfies the functional equation f2x is t of f of x. You can try this out with concrete matrices. Take the Laplacian L of a circular graph. Now compute TL. You end up with 2 copies of the Laplacian of the circle with half the number of vertices. Here is our main result. There is a universal limiting spectral function f to which the spectral functions converge in L1. The limiting function only depends on the dimension of the complex. This implies that the integrated density of states converges pointwise, implies that the density of states converges weakly. The result can be seen in the context of other universality results. There is first of all the central limit theorem in probability theory. It can be seen as a limit of renormalization map. Then there is the universality in dynamics, as the Feigenbaum story illustrates. In mathematical physics, there are similar constructs like in lattice gas models, where the renormalization map replaces a spin block with an effective spin. Here's the formulation of the central limit theorem of Lindeberg and Levy in a renormalization setup where in each step a sum of two identically distributed random variables is taken and normalized to get a new random variable. The limiting distribution is then the Gaussian distribution. If the random variables would be circle valued, then the limiting distribution is either the uniform distribution on the circle or then the uniform measure on a discrete subgroup of the circle. And we see here four major mathematicians who have contributed to the central limit theorem: de Moivre, Laplace, Lindeberg, and Levy. De Moivre, Laplace dealt with special discrete random variables where the renormalized random variables always have a binomial distribution. Lindeberg and Levy are the architects of modern general formulations. Here is the Feigenbaum-Fixbaum theorem as proven first by Oscar Landford with a computer-assisted proof. The renormalization map takes place in a space of smooth functions which are concave down, are even and take the value 1 at 0, and which are negative at 1 or minus 1. Examples of maps which satisfy this condition are 1 minus 2x squared or cosine pi x. It is a famous and important story. Many mathematicians have contributed. On this slide we see a few faces. Let's now look at the proof of the theorem. We only give the main points. A first observation is that the spectral function is the same if you take several disjoint copies of a graph. Now, since the barycentric refinement step puts several copies of a graph together, but then glue them along lower dimensional parts, the difference between the spectral function of the disjoint union and the spectral function of the refinement becomes exponentially small in the limit. But this needs to be justified. While we know that the boundary parts are small in size, we need to relate this to eigenvalues. Here is an important inequality which is due to Yoram last and follows from a theorem of Litsky. We can estimate the L1 norm of the difference between the spectra of two self-adjoint finite dimensional matrices in terms of the sum of the differences of the matrix entries. This result of Litsky can be found in a book of Barry-Simon on trace ideals. Yoram last modified this result in an essential way so that it can be used here. I learned the result from him as formulated in the last slide. In order to understand what happens when we connect different parts of a barycentric refinement, we need to know that if we cut an edge, then this changes the Laplacian only at 4 places. But that's pretty obvious. We also have to understand what happens with the number of simplices if we do a barycentric refinement step. The F vector transforms in a linear manner given by a matrix A whose entries are a factorial times a Stirling number of the second kind. This seems to be well known by combinatorial topologists. Here is the definition of the Stirling numbers. S and K tells in how many ways we can partition a set of n elements into K subsets. A set with 4 elements, for example, can be partitioned into 7 different ways into 2 non-empty subsets, 4 ways into 1 plus 3 sets, and 3 ways into 2 plus 2 sets. The matrix A is very interesting. For every eigenvector of A transpose, we know how the number of elements grows. Of special interest is the eigenvector of A transpose to the eigenvalue 1, which leads to the Euler characteristic. This eigenvector is just 1 minus 1, 1 minus 1, etc. Just as a side remark, we mentioned that for geometric graphs, the barycentric characteristics are 0 in half the cases. This is related to Poincare duality. The proof can be done also using Gauss-Bonnet, a Gauss-Bonnet formula for valuations. What happens is that for DEHN-Sommernville valuations, the curvature is a DEHN-Sommernville valuation. The DEHN-Sommernville relations have been discovered by DEHN, Sommernville, and KLEE, who we see here united. Here are 3 examples of valuations. The first is the Euler characteristic, the second is a barycentric DEHN-Sommernville valuation, the third is the volume. In each case, we also place the curvature values which add up to the valuation. In case the complex is the discrete sphere. suspension of a pentagon. The Euler characteristic is 2, the Sommmerville valuation is 0, and then the volume, that's the number of facets, which is 10. The Gauss-Bonnet theorem we know for Euler characteristics generalizes vastly, first of all to linear evaluations, then to multilinear evaluations. For the Euler characteristic, barycentric limit leads to the classical Gauss-Bonnet Chern theorem. By the way, the fact that for odd-dimensional graphs the Euler characteristic is 0 is a Sommmerville manifestation. Curvature is 0 then, but in a continuum it's usually not even defined. The proof of Gauss-Bonnet is in general very simple. We first have a curvature on the simplices of the graph. Now push all these values to vertices by distributing evenly. This gives a function along the vertices of the graph. This is what we call then the curvature. This pushing to the vertices can happen in different ways. For example, if we push the curvature from simplices along a function to the vertices, we get Poincaré-Hopf theorems. As realized by integral geometers like Banjoff, already averaging the Poincaré-Hopf indices gives curvature. That general principle holds in general too. We digressed maybe a little bit too much now, but let's go back to the spectral picture. Here's the picture in 1 dimension. We started with a cyclic graph of 4 elements and refined. We see how the spectral function converges nicely. We even see monotonicity with respect to the renormalization time m. In 2-dimensional case, where we don't understand the limit yet, the convergence is also more complex. The monotonicity still is seen to happen most of the time, but there are already violations. Here's a story in 3 dimensions, and we see even more clear violations of the monotonicity. Still, the convergence is pretty fast. We see only FG3, the third barycentric refinement, but the limiting distribution is already close to that green curve. Here is an inequality of Schur, which sheds some light on the structure of the spectrum. This inequality compares partial sums of the eigenvalues with partial sums of the diagonal entries. It's a very general inequality. It generalizes the equality we get when comparing the trace with the sum of the eigenvalues. The Schur inequality tells us, for example, that the limiting measure has no compact support in 2 or higher dimensions. It also gives us some idea about the density of states. If we replace the Kirchhoff Laplacian with another Laplacian, like the connection Laplacian, we can prove that that in the 1-dimensional case a mass gap develops. That's quite exciting. The reason is that both L and its inverse have norms smaller than 5. It's a general fact that L is always invertible then. And the limiting spectrum is therefore included in the interval -5, -1/5, or 1/5, 5. See the gap in the left. On the right we see a 2-dimensional picture where we don't understand the story yet. We don't even know whether the spectrum has one single gap. What is the limiting geometric space if you look at the sequence of barycentric refinements? We only understand the 1-dimensional case completely. The limiting space looks flat. When averaging curvature over patches gets 0. However, the curvature fluctuates more and more and also gets unbounded in the limit. The discrete spaces are locally Euclidean. Even if you start with a non-Euclidean situation, the dominating paths become Euclidean. And here's the story in 1 dimension. I've looked at this in my PhD thesis. The best way to understand the limit is to look at the story of on spaces of measure-preserving maps. The renormalization map now corresponds to a 2-to-1 integral extension of the map. In a metric space of measure-preserving maps, the limit has a well-known limit. The limit is well-known. For Neumann-Kakutani system. It is a measure theoretically conjugated to the adding machine on the compact topological group of dyadic integers. Here are the pictures of John von Neumann and Shizuo Kakutani. The space of dyadic integers is a very natural space. It is compact but still plays the role of the integers in the field of dyadic numbers. Its dual, the Prüfer group, is a quotient of the ring of dyadic rationals. The dyadic integers share properties from both the circle and the integers. They are compact, but there are units in since it's also the units in the field of dyadic numbers. As a comparison, the story is a bit reversed in the more familiar field of real numbers. The compact analog space is the circle, which has as the dual the space of integers. Here we see the comparison between the familiar real world and the dyadic world. What is special about the dyadic case is that it features the smallest translation, the adding machine, which is known in ergodic theory as the von Neumann-Kakutani system. In the real case, there are many rotations which can serve as translation. Both the circle as well as the dyadic group have a renormalization symmetry. They are chaotic systems in both cases. Bernoulli systems, in the case of the circle, it is Sx equal to 2x, the doubling. In the case of the dyadic integers, it is the shift. A barycentric refinement induces such a shift. We don't understand the quantum plane yet, the barycentric limit in 2 dimensions. Barycentric refinements of 2-dimensional complexes are more complicated. The vertex degrees grow exponentially under refinements. This makes description more difficult. We could call the quantum plane the limit of a triangulation of the plane under barycentric refinements. To do so, we need 2 commuting maps. These maps get refined and lead to a limiting Z2 action on a compact topological group. We start with 2 commuting measure-preserving transformations, S and T, while in 1 dimensions we make a 2-to-1 integral extension. We now triple the probability space. Then we redefine the maps S, T, V on the new space. This renormalization map has a von Neumann-Kakutani limit. Now we hope that we can realize a limiting almost periodic operator whose spectrum is the limiting distribution we have proven to exist, but we still need to work on this. This is it. For more information about this universality result, see the 2 archived papers from 2015. The picture seen on this slide shows a barycentric refinement of a wheel graph, and the colors indicate the nodal curves of an eigenfunction of the Laplacian.